Okay, hello everyone. Happy Thursday. This is the end of the fifth week of our class. We only have one more week. It's kind of hard to believe that. Um, Time flies by so quick. I'm in an 8-week course, so I have 2 more weeks. Well, I have 3 more weeks after this one. I can't wait for my class to be over with. I've learned a lot of good stuff in my class, but I just want my class to be over with because it's been a lot of work for me. I need a break. But I hope to see everyone in my Organic 2 class next semester. So if you're taking Organic 1, hopefully you enroll in the Organic 2. And we're just going to continue off where we left off on for Organic 1. I've had questions about the final exam. The final exam will cover chapters 1 through 10. It'll be comprehensive. So expect a little bit about from everything. It'll be 30 questions. You'll have 3 hours. Similar format. So expect about 3 questions per chapter. 3 times 20 or 10 would be 30. So you'll get about 3 per chapter. We might go into chapter 11 next week, but it won't be on the final. But if we have time to go into chapter 11, I'd like to do that. So we will have, Monday, Tuesday, and Wednesday, and I want to use our time as effectively as I can. Thursday is going to be left for you if you want to talk about your grade. I won't be able to calculate the grades though till Thursday though. And the reason being is I won't have all the final grades until Wednesday night. Well, I guess at 11:59 Wednesday. So just please keep on top of everything. We're coming to an end. If this is your last class of the summer, just enjoy the rest of your summer off. I know how it is taking classes in the summer. It's intense. I wish my professor was a little more lenient on the time like I am with you guys on the test. I'm only given 25 minutes for 20 questions. You guys are given 3 hours. If it was the professor that I'm taking, I bet she'd only give you about 40 minutes to take these exams. So, you're lucky. Does anyone have any questions for me? And the reason why I give you time, because I feel stressed out with that limited amount of time. I don't know if you guys would, but that's just me. I don't want time to be a factor as far as like stress, because I don't believe in, just rote memorization. I believe in understanding. And sometimes you need to think through the question to understand it. So we left off on 17. Did we complete 17? Let me see. And yes, we did. So that's the answer to 17. I will post this homework today. So we're on 18 now. So it says, let me see, I'm going to just make sure I'm on 18. Yeah. So it says for the reaction shown, draw the product of 1 mole of reagent adding across the triple bond, and then draw the product of a second mole of reagent. So we have 1 equivalent and then we have 2 equivalents. So you can just imagine with the 1 equivalent, I'm just going to look at it from the triple bond point of view. Everything else is, it's all there. It's not going to really contribute anything. But we're going to have that chlorine come in here, just like we did with the double bond. And then the chlorine can either come in here. If it goes in there, it'll be released here. If it goes in here, it'll be released here. So we're going to draw product A now. And then product B will just be the same thing. We're just going to add another chlorine to it. So like I said, if you put the chlorine here, then you're going to have to put it in this position. You have the hydrogen. And if we think about product B, it's going to be the same thing. We're just going to add 2 more chlorines to it. So I'm just going to delete that right there. And here is product B. All right, so we'll go on to question 19. Question 19 deals with ozonolysis. Let me see. So we have some type of ozonolysis reaction. Remember, what's going to happen is we have some type of triple bond, we have some type of R groups, and this is going to bust. And when that busts, we're going to have a carboxylic acid group. So, and we're going to get it on both ends. So it shows us that triple bond. We know that that's going to bust right in the middle right there. So for product A, you know, it doesn't matter which one you draw first. We're going to have that phenyl group with the carboxylic acid right here. And for product B, you know, we'll have that carboxylic acid group followed by this group right here. It doesn't matter if you put this for B or A, you know, so that's what's going on right there. And that's typical with your ozonolysis. So when you saw O3 and those reaction conditions, you know, that's what we're gonna get. So. I just had to refresh my homework. Mine froze on me. So 20, it wants us to draw the major organic products, and what you're going to draw is this. You're going to draw this one as well. All right, so that's 20. I actually had to refresh 20 a few times for that one to show up. Wasn't showing the starting materials for some reason. 21, it says draw the structures of organic compounds A and B. So we have this acetylene. We have a triple bond here. There's a hydrogen here and there's a hydrogen here. And you have sodium at mid. You know, we have this sodium at mid right here. 1, 2, 3, 4, 5, 6. -1. What's going to happen is, you know, it's going to take this, it's going to come here. And once that comes here, then we're going to have this. And we're going to do an SN2 reaction where we have, I'm just going to draw it like this, actually. Well, it'd probably be better to put on the other side. It's going to go here through SN2. This is going to go. And what we're going to get is compound A, which is going to be so you have 1, 2, 3, 4, 5. So I got to get rid of 1. in the wrong place. There we go. So that's what we have for A. And then to get to B, this is a 1 here, not a bond. To get to B, we're using this H2 in the Lindlar's catalyst. Remember, this is only going to take it down to the double bond. So we're going to take this to a double bond. We'll reduce that down. So we're going to go to a double bond here. So we just have the same thing, which is a double bond 1, 2, 3, 4, 5. So that's it for compound B. And then to go further, then, they add water in that H3O plus, and then that reduces that down to an alcohol. But we don't have to show that step. I just want to see anything in the chat. All right. Let's go to 22. Kind of similar situation here. Let me think about this. One, 2, 3, 4. 1, 2, 3, 4. So it says in the reaction box, place the reagent and the conditions from the list. Let me see about this. So the first step, we want to use a sodium with ammonia. And then, the second step, we're going to use the 1 equivalent of bromine, because we only see 1 bromine on each methyl group right there. Now, if we use 2 equivalents, we'd have put, if we would use 2 equivalents, it would have looked like this. We'd have had 2 bromines here. Likewise here. But we're only using 1 equivalent, so we're not putting that down. Actually, we should have used, I'm just curious, we should have used the H2 in Lindlar's catalyst. Let me see. So that reduces that triple bond down to a double bond. Let me get my textbook out real quick. Just hold on. Just check those answers to see if they're right. So did that work when you put the H2 in the Lindlar's catalyst? I don't see anything in the chat that said it didn't work. So. Did that work? Did anyone get this option to work, the H2 and the Lindlar's catalyst? If you go to 427, 427 has a review of the reactions. That's where I'm getting a lot of my information from. Okay, so now I'm just gonna put in here, to use the NaNH3. But note that you could do this too. Remember, we talked about that a lot. Taking a triple bond to a double bond, you use the Lindlar's catalyst. And if we want to take this, further, we just use H2 and palladium. That will get us to the single bond. But if you go to page 427, I don't know if it's the same in the electronic book, but on mine, it has a review of reactions, and it's pretty good, to be honest with you. And then if you go on to 428 and 429, they show you more reactions like this. And they show the Lindlar's catalyst going from triple bond to double bond. So, all right. So that was 22. Let's go to 23 then. Let's see what 23 wants. Is that it? Oh, no, I gotta refresh my thing. All right, so let's go to 23. This will be our last question of this homework. And then we'll take a 20-minute break. We'll take a 10 to 15 minute break in between this and the chapter 10. So we have this right here. So what is our first step? We see what the products are going to be. So what we're going to want to do is, let me count how many carbons we have in the products. We have 1, 2, 3, 4, 5. So in this one, we have 3. And then, in one of the subsequents, we have 2. So we know we're going to add this at some point in time. But to get there, we're going to have to use the sodium NH2 and the NH2. Why? Because sodium is a positive, right? So if we just draw out NH2, this is a minus. 1, 2, 3, 4, 5, 6. So 5 minus 6 equals minus 1. The sodium is a plus 1. That counter ion's right here. So it equals 0. Then we're going to take this like this. This is come here. So this is going to be your step 1. Then we're going to go to an SN2 reaction. And this is going to jump off. The bromine's going to leave. Okay. Then we're going to reduce it. And we're going to use the same step as before. We're going to use sodium. So we can use sodium ammonia to reduce this down to the double bond. So this reduces to double bond. And what we're talking about that is we're talking about this right here. So, you know, you'd have this. Right, the double bond. And then we're going to add KMNO4. What is that going to do? Let me look in the book real quick. KMNO4 is going to add the OH groups in a syn fashion. So KMNO4, you know, we're going to add the OH in a syn fashion. So here, you know, here's one. Let me put this down, otherwise you might get, so here's 2, here's 3, and here's 4. And then they show the products, you know, so I'm not going to redraw the products, but you can see, well, they are added in a syn fashion. But it doesn't, you know, so we're going to get the RR or the SS. And the reason why they're not showing you as a syn, so I'll show it to you. I don't think the book does a good explanation on. So we're going to have either the OHs here with that methyl group. I'm just going to draw that methyl group. You know, it's implied that we have a hydrogen coming off here, we have a hydrogen here. I'll just draw this one. This is the RR. So you have an R, you have an R group here. So you got 1, 2, 3. This would be R. Yep. So you have RR and then you have SS. The reason what they're doing is this can rotate, right? On a single bond, this can rotate. So that's why, you know, they're not showing it to you the way I've drawn it right here. They're trying to confuse you, to be honest with you. They're showing this as it rotated up. This would be structure number 1, what they're showing. I don't like that, but you know, it is what it is. But these OHs are going to add in a syn fashion with KMNO or KMNO4, which is potassium permanganate. And that's it. Any questions on this? Someone, before I let you go, let me save this. Someone had a question on a previous chapter. Let me yeah, we want to keep these annotations, otherwise we're not going to be able to share them. So before we take a break, we'll go over that student's question. I'll save this. Pull up my email real quick. Pull up the question. Let me pull this up. I do apologize for not having the first part of chapter 8. It didn't save correctly because this, like I said, these computers are being we're getting new computers either this summer or next semester, and we need them because they are starting to fail. Every time that I put my computer in sleep mode, I have to restart the computer, and that's not right. So that means if I don't save something, it gets automatically deleted. Or if it just goes to sleep on its own, you know, it gets automatically deleted. And that has affected me. So I don't really appreciate that, but that's why we're getting new computers. So let me see. Let's see what the question is. Question. Oh, I see. I see what's going on. Yeah. Let me see. So the reason why it marked it wrong, okay, let me show it to you. You got to pay attention to these arrows. Let me see. I'm gonna stop screen sharing just for a second. I'll put this on my other screen. Oh, I was thinking. I'll share that. So the reason why it marked it wrong on your question is just the way that the arrow should be going. So pay attention. Well, actually, let me see. Yeah, so these arrows should be going. See how this? Let me blow this up. See how this arrow is going this way? This arrow is going this way. I'll put an X, and this arrow is going this way. So that's why I did it to you for. So it was the way that the arrows were drawn. Discard that. They really want you to pay attention to the way that the arrows were drawn. All right, any questions? Okay, so we're going to take our 10 to 15 minute break and we'll be back and we'll finish, we'll begin chapter 10. Yeah, it happens. I make simple mistakes too. So, luckily, it's homework. There's a lot of questions to it and, you'll be fine. All right, so I am re-recording now. We just got back from our break. We're going to move on to chapter 10. We just finished the chapter 9 homework. So please keep in mind the due date for chapter 9. Let me see when that's due. It's due, let me see. Chapter 9 is due on June 25th. So that would be Saturday. So chapter 9 is due by Saturday, 11:59 p.m. So let's go into the screen share. Chapter 10 will be on the exam. I'll probably post the homework questions for chapter 10 either today or tomorrow. For sure, they'll be up tomorrow, probably today, but it won't be till the evening. We'll get to the homework questions on chapter 10 on Monday. And Tuesday, we'll probably be able to finish it up on Monday. So I just want to get the homework questions out there for you in case, you want to work on your exam, you can have the homework completed because I plan on posting the exam sometime this weekend. I'm going to go by the syllabus and I'll probably make the exam on Friday and post it Friday, so you'll have some extra time to do it. Okay, so let me see. It says I'm sharing, so that's good. So we're going to be learning about radical reactions. And remember, from way back when we talked about homolytic cleavage. There's heterolytic cleavage and homolytic cleavage. The homolytic cleavage just means one electron is moving. Let me get my pen, show it to you. So you have one electron here, and you have one electron here. And typically, you're going to be seeing something like this. Or something like this. So we're generating some radicals. It says, note the single barbed or fishhook arrow is used to show the electron movement because we're only showing, one electron being moved. This would be an example of a hydrolytic cleavage right here. But we're not talking about that for this time. We're just talking about the homolytic cleavages for the radicals. So recall the orbital hybridization in carbocations. So this carb anion, this is sp3, which is trigonal pyramidal, because these electrons are pushing down on these bonds right here. So that's what's going on. And right here, we have a carb cation. And with a carb cation, this is all in a plane right here. That's why they have it trigonal planar right here. Now, you can imagine if we just had one electron, see, two electrons are going to push it down more. One electron is not going to push it down as much, right? It'll be a weaker push down, and they show that to you right here. So it says radicals appear to be trigonal planar or shallow trigonal pyramidal. So it's somewhere in between. So it's rapidly interconverting because there's only one electron here. Now, if there's two electrons, be able to push this down pretty good. If there's no electrons, there's a carbocation, it'd be trigonal planar, but it's somewhere in between. It says radicals are neutral. They have no formal charge, but they still are electron deficient, so an incomplete octet. Radicals follow the same stability trend as carbocations. So this would be the most stable radical, a tertiary radical versus secondary versus primary versus methyl. And we saw this before when we talked about, the carbocations. So bond strength is inversely proportional to the carbon radical stability. The more stable the resulting radicals, the weaker the bond. And we can see this right here. Remember, this was the most stable from the previous slide, the tertiary radical. Here we see that, the methyl group would take the most energy to break that apart because it's not as stable. But there's still a lot of chemistry that's done, with methyl radicals. So just like carbocations, we talk about something like this. We can jump the charge here. And, we'd have this right here. And this is resonance stabilization. We draw this something like this. But we can have the same thing with these radicals. Or if this comes here, we'll just show one barb. And we have one barb here, and we put the other barb right here. And we get this. Well, it says the more resonance delocalized a radical is, the more stable it is. So benzylic radicals, and here's your benzyl group, are more stable than allylic radicals. And this would be an example of an allylic radical right here. They're more stable than allylic radicals because the radical is delocalized over more carbon atoms. We can just keep on moving this, and they show you how to do it here. We can move it here, and we can move the radical here, and that radical can be moved here, and then finally it can be moved here. So it's delocalized over all these different carbon atoms, so it's more stable. It says resonance stable radicals are more stable than the tertiary radical. And we can see, okay, here's our tertiary radical. This one has resonance right here. And it's 364 versus 381. But when we add the benzyl group to it, it goes down to 356 because there's more carbon atoms that radical can be stabilized over. It says vinylic radicals are especially unstable, as with vinyl cations. A radical in an sp2 orbital is less stable than one in an sp3 orbital. They show it to you right here. Here it'd be an sp2. Here's your sp3, 464 versus 364. So it's 100 kilojoules per mole difference. It says like ionic mechanisms, radical mechanisms follow patterns, but radical mechanisms are distinctly different. For example, the radicals do not undergo rearrangement. So in this case, remember, we could move this over here. We could move this over here to produce a more stable carbocation, but we're not going to do that for radicals. This radical will not rearrange to produce a more tertiary radical. So radical mechanisms follow 6 key arrow pushing patterns, and we're going to show that to you on the next slide. So here's the patterns. We have a homolytic cleavage initiated by light or heat. So if they're going to go by heat, they'll indicate by that delta right there, and light is by h nu. And that's Planck's constant times the frequency. Addition to a pi bond, and we can see that pi bond right here. So that's going to form that single bond right there that they show right here. And then you have that one single barb arrow pushing that radical right, or that electron right over here. Hydrogen abstraction, it's not the same as a proton transfer. We're abstracting the hydrogen from this group over here. We can do the same thing with halogen abstraction. So you can just imagine this being chlorines. This would go here, and this would go here, and that X now would be chlorine. We have elimination as the reverse of addition. The radical on the alpha carbon is pushed towards the beta carbon to eliminate a radical atom or group. So we form this double bond right here, and this group is a good leaving group. Coupling, the reverse of a homolytic cleavage. So remember, on a homolytic cleavage right here, we're breaking the bond. Here, we're forming a bond. So, there's some grouped relationships among these 6 patterns, and you see there are only 3 processes, forward and backward. So you can have a homolytic cleavage, you can have a coupling, you can have addition to a pi bond. Here would be this. You can have elimination. You have hydrogen abstraction. obviously elimination would go like this. It's getting kind of small, so I'm just gonna go this way. So they want you to practice that. It says the steps in a radical mechanism are classified. So you have, first you go through the initiation, termination and then termination or propagation. So initiation step is one where the radical species are formed from a non-radical species. Think about this as chlorine. We have our homolytic cleavage right here. So that would be our initiation step. The last step, the last step would be termination right here. Propagation occurs when radical reacts with a non-radical species. So this is our second step. So we have a non-radical species right there. It's addition to a pi bond, and it's propagating. We talked about the addition to a pi bond, hydrogen abstraction, halogen abstraction, and elimination. These are all forms of propagation. And finally, we come to termination, and this occurs when two radical species react to form a non-radical species. You can just imagine this. So let's talk about, a reaction that we might see. So we have methane, we have chlorine. This would be a gas right here. We react that with light, and we form methyl chloride. So initiation, the chlorine radicals are created. So they're created through a homolytic cleavage. So we create our two radicals right here. Then we're going to propagate that. So we have our radicals, we're going to, in this case, they're showing a hydrogen abstraction. It forms a carbon radical right here. And then we're going to go with the halogen abstraction. So it gives the product and regenerates a chlorine radical. So you can see how we just keep on regenerating these chlorine radicals then. If we regenerate it, we can continue on, keep on producing more of this product. And then termination occurs when the radicals collide or couple. So here we're coupling them. We're forming this chlorine, or forming methyl chlorine. And then we can also have the coupling. It destroys the two methyl radicals right here. So now we're not forming methane, we're forming ethane. So the sum of the propagation steps gives the net reaction. So here we have hydrogen abstraction. You have this with this radical. And then they're not showing this, but they showed it on the previous slide. That's how you get these two. And you have the halogen abstraction. But notice what we can do. We have them on both sides, right? With that CH3 radical, CH3 radical. So we can eliminate that. I'm going to erase all this. It's getting a little messy. So we can eliminate stuff on the left hand or the product side and the reactant side. So the net reaction would be just bring down what's ever left. For propagation of the chain reaction, the products for a later step serve as a reactant for an earlier step in the mechanism. You can see how this will come up here. This can come here. So chlorination of methane, polychlorination. So polychlorination is difficult to prevent, meaning, adding more than one chlorine onto it. Methyl chloride is more reactive towards radical halogenation than methane. So think about this. So methyl chloride, which is here, is more reactive towards radical halogenation than methane. So that means it's going to be more likely to go this direction. So you need excess methane relative to chlorine for monochlorination to be the major products. So it all depends on what you want to make. So if you want to make just methyl chloride, you have to have this in excess. Otherwise, if you just have it in the 1-to-1, you're more likely to go down to here. So radical initiators possess a weak bond that cleaves homolytically with heat or light. So dihalides, alkyl peroxides, and acyl peroxides. So they're just showing you some groups that really can form radical. Anytime you see an oxygen like this, you're most likely you're going to get a radical. And where do you see that? This is a peroxide, hydrogen peroxide right here. So we're going to be forming radicals. It says the acyl peroxide is most reactive and is effective at 80 degrees Celsius. You can see that, look at the bond energies, 121 versus 159 versus 243. So we go into this thing called radical. So if we want to inhibit a radical, so radical inhibitors react with radicals and prevent a chain process from initiating or propagating. Stabilized radicals and compounds that easily form stabilized radicals are good inhibitors. So let's just say that again. So stabilized radicals and compounds that easily form stabilized radicals are good inhibitors. So oxygen is a diradical and will react with two other radicals. And hydroquinone will also react with two radicals. It says radical reactions are very slow in the presence of oxygen. And typically you see oxygen drawn like this, right? That's how you went from that one to that one. Hydroquinone undergoes hydrogen abstraction to form a resonance stabilized radical. Okay, it doesn't want me to erase that anymore, so we'll take it like that. There we go. So we have our hydrogen abstraction. This is resonance stabilized. We can push that, right? Here we go through another hydrogen abstraction here. Oh. That R group would probably be over here, you know. Then you can form this benzoquinone. So that's what they mean by resonance stable radical. So now we've had two examples, hydroquinone and oxygen. So here's your two examples. So if we want to determine whether a process is product favor, we must determine the sign for delta G. So delta G equals delta H, which is your enthalpy form, plus your entropy form. So in a halogenation reaction, entropy is negligible. So if that's negligible, that means it's basically going to zero. You know, it's very close to zero. So that's what it means by it's negligible. So the number of reactants equals the number of products. Here we have two molecules of this. It gives off two molecules. So delta G is approximately equal to zero. All right, delta H, that means because this is basically going to zero. So if we have 2 and 2, because remember, entropy is the amount of disorder. And to get more disorder, we have to go from like 2 to 3 or something bigger than 2. You know, we'd have to have a number bigger than 2. In this case, we don't. You know, we have 2 on one side and 2 on the other side. That's why, you know, we're putting a 0 in for entropy. And that's why that's how delta G equals the enthalpy term. I meant to say we're putting a 0 in for the entropy term. So, you know, we can estimate the value of delta H based on the bond dissociation energies for the bonds broken versus the bonds made. So sorry about that. You'd have this go on first. You have this, and you could extract one. And finally, it come in contact with one like that. So bond dissociation energies are relevant bonds, and they show it to you right here. This XX would be 159 for fluorine, 193 for bromine, 435 right here if this were fluorine, chlorine, bromine. So it gives you a list of BDEs. I guess here, this is all just this, this is just a hydrogen from a methyl group. Here, this X stands for either fluorine, chlorine, or bromine. And here, this X is fluorine, chlorine, or bromine, or iodine. This is all the same. So halogenation thermodynamics examples, you know, we have all these numbers from over here. So if you you'd have to add them all up or subtract them. So you take bonds made minus bonds formed. So fluorination is so exothermic, it is not practical, it's too violent. We see that we have minus 431. Iodination is endothermic, so it's not thermodynamically favored. We see that we get plus 55. So the only halogenation we have left is chlorine and bromine. That's practical. So again, to get that, you just take your bonds formed minus your bonds broken. So both chlorination and bromination are exothermic, they're favored. The first propagation step is a hydrogen abstraction. And they show it for you for chlorine and bromine. And this is this step right here. Minus 1, but notice this is plus 42. So that means you can have more control when it's bromine. The second step is halogen abstraction. And net for this is minus 117. You just added them together. So, but delta H for the first step of bromination is endothermic. So you can have more control at a smaller number. And they do a good job right here. So the bromination is much slower than chlorination. This means bromination is more selective. You can see right here, there's a very low energy of activation. We just see this right here. And this one, looks to be about 4, 5, 6 times as much as the chlorination activation energy. So that's why you can be more selective with the bromination. It takes a higher, and you have to have it's an endothermic reaction for the first step. So with substrates more complex than ethane, multiple monohalogenation products are possible. Here we see we have 2 hydrogen atoms right here. Here is 6 hydrogen atoms. You got 3 and 3 is 6. So 2 monohalogenation products are possible for propane. So chlorine is indiscriminate. A significant amount of each product is formed. They don't say how much, but significant must be about a 50-50. Maybe one's 45, the other one's 55, but you get them in a significant product because it's indiscriminate. So it doesn't care if it takes it from here or here. On the other slide, it's 60-40. And the reason why this is a little slightly higher is because this would form a secondary radical, right? If we just look at this versus this is more stable. So if that's more stable, you're going to get more of this product. So we can see this right here when looking at the potential energy diagram. The secondary radical is more stable than the primary. Just like a secondary carbocation is more stable, the secondary radical is more stable. Bromination is much slower, and so it is much more selective for the more reactive secondary carbon. And remember, the difference was it had a much higher activation energy, didn't it? You know, if this is bromine, you know, the chlorine was somewhere up here. You know, so that higher activation energy tends to now favor the secondary radical a lot more than the primary. And that's because of due to the bigger hump that it has to get over for the activation energy. Let me just look up that definition for you again. So the Hammond postulate says, and this is from section 6.6, if you want to go back to read it. It says, in an exothermic process, the transition state is closer in energy to the reactants than to the products. So its transition state is closer in energy to the reactants than to the products. And therefore, the structure of the transition state more closely resembles the reactants. In contrast, the transition state in an endothermic process is closer in energy to the products, and therefore the transition state more resembles the products. So for this, we have, for the bromine, the transition state would more resemble the products, which would be the endothermic reaction. So that's what another reason, that's, you know, the main reason why we get the 97%. Plus the secondary is more stable, but you know, even more so, this is more explained, you know, really explained by the Hammond postulate. And the next slide actually does a good job of explaining this. It says, focus on the hydrogen extraction, the rate determining step. The transition state will more like the reactants, more like the products, whichever is closer in energy. So bromination transition state resembles the products, and we can see that right here. And the chlorine transition state resembles the reactants. And from a graphical perspective, this says this bond is only beginning to break with the chlorine, and this bond is almost completely broken with the bromine. I think this is a good time or a good place to leave off because we're getting into some stuff I don't want to rush through. So we're going to leave off here, and we'll even pick it up on Monday where we left off at. So on Monday, we'll finish this chapter. We'll go into the homework. We'll for sure have the homework done by Tuesday. So I'll probably put the due date for the homework on Tuesday. You know, the test due date will be Wednesday. So if we have time, you know, we're going to go into chapter 11, but we won't have any chapter 11 homework. I might assign some chapter 11 homework, but I'll make it, I know we might have some chapter 11 homework, but we'll be able to do it all in class. You know, we're not going to assign chapter 11 homework, then you know, not going to be able to do it on Thursday, but there will be no chapter 11 homework, or not homework, but chapter 11 questions on the exam. So the exam consists of chapters 1 through 10, about 3 questions each. You know, some questions may, you know, say, oh, I see a question that could be from chapter 1. Well, a lot of this material is interrelated to each other. So please keep that in mind. If you have any questions, please stay behind. You're done for the day. Have a great day, and I'll see you on Monday.